John Physics, Chapter 1, Unit and Measurement.
Hey, welcome to Black Tutorial. Our aim is to ensure you pass your exam excellently, having above 280 or 300.
Chapter 1, Unit and Measurement today. It includes fundamental and derived quantities, SI units and unit system, dimensional analysis, significant figures, least counts and measuring instrument, errors in measurements, and some practice questions. What are fundamental units and fundamental quantities? So fundamental quantities or base quantities is just like foundation, fundamental, the base. So nothing is built on it. They are the basic, the independent. They are the basic, the independent. Like they cannot be expressed in terms of other quantities. While the derived quantity, on the other hand, are obtained by combining fundamental quantities through multiplication or division. Examples of fundamental quantities include, we have 7 major fundamental quantities in physics, which are length, mass, time, electric current, temperature, amount of substance, and luminous intensity. We have length. The SI unit of length is meters. The symbol is small letter m. Mass, the SI unit is kilogram. The symbol is small letter kg. Time, the SI unit is seconds. The symbol is small letter s. Electric current, the SI unit is ampere. The symbol is capital letter A. Temperature, the SI unit is Kelvin, not degrees Celsius. Kelvin, which is capital letter K. Amount of substance, the SI unit is mole. The symbol is small letter MOL. While luminous intensity, the SI unit is candela, which is small letter CD. Those are the 7 fundamental units in physics. 3 of it are more important for dimensional analysis, which are the length, mass, and time. So for the derived quantities, we have area, volume. Area is length times length, that's meter square. Volume is length times breadth times height. But all of it has the unit as meter, so it's taken as length times length times length. That's meter cube as the unit. We have velocity, length over time, which is meter per second. We have acceleration, which is length over time squared. That's velocity over time. Acceleration is velocity over time, and velocity is length over time already divided by time. When you can have it to be length over time multiplied by 1 over time, then you have your length times 1 over t raised to power 2. So we have it to be meter per second squared. We have energy to be force times length. We have force to be mass times acceleration, F equals ma. That can just stick to you. We have power to be energy over time taken. We have pressure to be force over area, and we have density to be mass over volume. Going up to SI unit and systems. In physics, measurement is a very important thing. It makes us know how much of this property there is. And without units, there is no complete measurement. I can just say 5 volts. But if I say 5 meter, you know I'm talking about a measure of length. I can just say 15 watts. But if I say 15 seconds, you know I'm talking about how long it takes an event to occur. So basically, without units, no measurement is complete. So we have different units. We have CGS, centigram, gram, and seconds. These are based on the 3 major fundamental quantities I talked about. MLT. In this system, the unit of length is centimeter, the unit of mass is gram, and the unit of time is seconds. Then we used to have MKS, that's the meter, kilogram, seconds. In this system, the unit of length is meter, and the unit of mass is kilogram, and the unit of time is seconds. And we have SI unit, which is this international system of unit. It is the most widely used system of units. It is an extension of the MKS system and includes 7 basic units. So those are the units we talked about. There are also the FPS food pound system in the United States, but they are no longer useful for us as Nigerians. The SI unit is the modern metric system adopted internationally in 1960. So these are some of the common derived units with their special names. We have force, the unit name is Newton, and the symbol is N. It is also kilogram meter per second squared. Energy, which is work, is measured in joule. The symbol is J, and it is also Newton per meter. Newton times meter dot is multiplication. Newton meter. We have power, which is watt. The symbol is W, and it is expressed in joule per second. We have pressure, which is Pascal. Symbol is PA, and it is expressed in Newton per meter square. Frequency is Hertz. Hertz means per second. S raised to power minus 1. Electric charge is in coulombs, and it is A dot S, that's ampere times seconds. Voltage is measured in volt. Symbol is capital letter V, and it is also joule per coulomb. Resistant is ohm, and the symbol is like an inverted U with wings, something like a magnetic hook or something. So we have the expression to be volt over ampere. Going to 3, we have dimensionals and dimensional analysis. The dimensional formula of a physical quantity shows how it depends on the fundamental quantity, especially mass, length, and time. So the dimension can be written as m raised to power a, l raised to power b, t raised to power c. So for example, lt raised to power minus 2, that's acceleration, it does not require m. So if you're writing it, you can write something as m raised to power 0, anything raised to power 0, where you multiply this one, if you see with the rest. So you can write m raised to power 0 or just omit it totally. So using of dimensional analysis, we use it to check the correctness of an equation. Both sides of an equation must have the same dimensions. That's the principle of homogeneity. Example, check if s equals to ut plus half at squared is correct. On the left hand side, the dimension of s day distance is l, that's length. On the right hand side, ut, you can recall that in order for anything to be able to add together, they have to be the same. For example, you cannot add 2 orange to 2 apple, and you say you have 4 orange apple. It does not add up. So before you can add any of these things together, they have to be dimensionally correct, which is why ut, when we do the dimensional analysis of this ut, l t raised to power minus 1, that l over t times t, the t will cancel out, which leaves us with l. Same thing happens for half at squared. Half is just a constant, it does not matter. Or we have a and t raised to power 2. We have lt raised to power minus 2 multiplied by t raised to power 2. From our knowledge of sword, you know that minus 2 plus 2 gives you 0, which will leave you with l. Since both sides have dimension, which is l, then the equation is dimensionally correct. Convert units from one system to another. That's another use of dimensional analysis. So if an engineer wants to convert units, maybe you go to work in another country, you need to convert the unit. Knowledge of dimensional analysis helps you to easily convert the unit. So derive relationship between physical quantities. Can establish relationship by analyzing the dimension of the involved quantities. So we have quantities like area, which is length times length, L raised to power 2, volume, length times breadth times height, L raised to power 3, velocity displacement over time, that distance with the direction over time, that's L t raised to the power minus 1, acceleration L t raised to the power minus 2, force, mass times acceleration, m L t raised to the power minus 2, momentum, mass times velocity, that's m L t raised to the power minus 1, energy, force times distance, that's ml raised to the power 2 t raised to the power minus 2, power, energy over time, ml raised to the power 2 t raised to the power minus 1 minus 3. We have pressure, which is force over area, m L raised to the power minus 1 t raised to the power minus 1. Mass over volume, which is density, we have m L raised to the power minus 3. Impulse, the formula is force times time. We have it to be m L t raised to the power minus 1. You can notice that that is the same dimensional formula for momentum. So impulse is dimensionally equals to momentum. In case you keep it in equation, you can just memorize that and it saves your time. Frequency is 1 over time, which is t raised to the power minus 1. Going to significant figures. Significant figures are all the digits in a measurement that are known with certainty, plus the first uncertain digit. They indicate the precision of a measurement. So we have 25.34 centimeter as 4 significant figures. Significant figures like figures that are not 0 when they come up, they are significant figures. So we have 4 in the first example. So we have this second example to be 0.00456 gram. Everything we'll start counting where we have the first figure that is not 0. That's 1, 2, 3, 4, 5, 7, 8, 9. But we have yet to be 4, 4, 5, 6. That is 3 significant figures. Now, we have 100.0 meter. It has 4 significant figures. Here is the reason, because 1 is a significant figure. So it shows it validates this 0 and this 0. And anything after the point, any 0 they have add after the point is called trailing zeros. So they are added as significant figures. We have 1, first 0, second 0, and third 0 after the points. So we have 4 significant figures in that example. Rules for determining significant figures. We have non-zero digits are always significant. 0 between non-zero digits are significant. So, for example, 1002 are 4 significant figures because it is encapsulated, it is inside non-zero digits. Rule 3. Leading zeros before first non-zero digits are not significant. That's basically it. Trailing zeros after the decimal point are significant. So any zeros after the decimal point, they are significant. And their reason for putting the zeros is to tell you the accuracy of the measuring instrument. So it is not just written for writing's sake, it's to tell you the accuracy of the measuring instrument. 5. Trailing zeros in a whole number without a decimal point may or may not be significant. For example, 1200 has 2 significant figures. Decimal point indicates all are significant. For example, 1200 point should has 4 significant figures because there is a decimal point there. It's trying to tell you that the 4 digits are significant. 1.2 times 10 raised to the power 3 has just 2 significant figures. The scientific notation removes the ambiguity. So take note of the rules and you should be able to bash every significant figure question. Lead count and measuring instrument. So basically for measuring length. For measuring length, we have meter rule, we have vernier caliper, we have micrometer screw gauge. For measuring mass, we have we have weighing balance, like the beam balance, or measuring weight, which is force, we have spring balance, or measuring time, we have stop watch or stopwatch. So the least count of a measuring instrument is the smallest measurements that can be accurately taken by that instrument. For example, your protractor that you use your asset, it is 1 to 90, I guess 1 to 90, 1 to 180. So it is measured 1 1. The tiny lines inside is 1 1 each. So the least count of the protractor is 1. Now, formula for calculating this count is value of smallest division over number of divisions. The importance of least count is to determine the accuracy of measurements. The smaller the least count of an instrument, the more precise the instrument is. It must be known before using any measuring instrument, and it affects the number of significant figures in measurement. That's what I said earlier. They include the significant figure for us to know the measure, for us to know the measuring accuracy of the instrument. So measuring instrument and their least count include meter rule, which is 1 millimeter. 1 millimeter to make 10 millimeter now makes a centimeter. And that's how the measurement continues. For a meter rule means 100 centimeter. Vernier caliper least count is 0.01 centimeter or 0.1 millimeter. It is used for measuring internal and external dimensions. Micrometer screw gauge, 0.01 millimeter. So that is most accurate, most precise instrument. It can measure very small dimensions like a very thin paper. Stopwatch can measure up to 0.1 seconds or 0.01 seconds. Measuring cylinder, thermometer can measure up to 1 degree Celsius or 0.5 degrees Celsius. Protractor measures 1 degree angle, and beam balance measures 0.1 gram based on the build. So this is the vernier caliper. It has internal, can be used to measure internal and external diameter. The upper jaw are also called internal jaw. It can be used to measure the internal diameter of a given instrument. For example, if you open the tin of your milk and you want to know the internal diameter of that tin, you can use the upper jaw of the vernier caliper to measure that. So anytime you hear what it is for measuring internal diameter in your question, just know that your answer is vernier caliper. So you have the main reading scale, you have the vernier reading scale, and for your reading, you just need to know your main reading scale plus vernier reading scale times your least count. The micrometer screw gauge is used for the least measurement. It has the anvil, the spindle, and the H scale. For standard micrometer, the pitch is 0.5 millimeter or 1 millimeter. The tabular scale division is 50 or 100. For your reading, you just know the pitch scale reading plus the circular scale reading times the least count. So, for example, if you have your pitch scale reading PSR to be 4.5 millimeter and your CSR, circular scale reading, to be 20 division, and you know the least count of your micrometer screw gauge is always 0.01 millimeter, they might not give you that. You have to know it. So you simply put it into the formula 4.5 plus into bracket 28 times 0.01 and gives you 4.78 millimeter. And the zero error of a micrometer screw gauge, when the jaws are closed and the error of the circular scale is below the reference line, and you subtract the error from your reading. When the jaws are closed and the 0 of the stapler scale is above the reference line. Above, add, below, subtract from whatever you get as your reading. So we have errors in measurement. We have systematic errors. Those are consistent errors that occur in the same direction, and they can be easily corrected when identified. Then we have the examples are instrumental error, faulty instrument, zero error, calibration error. We have environmental error, which is effect of temperature, humidity, or pressure. And we have personal error, which are error due to parallax, reaction time, and bias. So we have random error, which are unpredictable variation in measurement that occurs without any pattern. It occurs randomly in magnitude and direction. They cannot be easily completely eliminated. They are reduced by multiple reading and calculating the average. That's why in your chemistry laboratory, most times they ask you to take 3 readings and you find the average, just because of this random error. We have gross error, which are human mistakes such as misreading the scale, recording wrong value, using wrong formula, and calculations errors. Next, we have accuracy versus precision. We have accuracy to be how close a measurement is to the true or accepted value, how close it is to the true value. While precision is how close multiple measurements are to each other. So the reference of accuracy is to the true value, while the reference point of precision is to each other, to other measurements that the same instrument make. So key points: accuracy, measurement can be accurate but not precise, can be precise but not accurate, can be both accurate and precise, which is the ideal, and can also be neither accurate nor precise. That one is the off. We have absolute and relative error. Absolute error is measured error minus the true value. Relative error is measured error is the change in error, change in measurement over true measurement. That's change in measurement is the absolute error. That's what you measured minus the actual true value all over the true value. That's relative error. But percentage error is when you express the relative error in percentage. That's changing x, which is what you measured minus the actual correct measurement all over the actual correct measurement times 100. So try your hand on this. Try your hand on this. If the true length is 50 centimeter and the measured length is 49.5 centimeter, the absolute error will be absolute. Whenever you see this slash sign, it means that you don't care about the negative sign. You know, this would have given us negative 0.5, but we don't care about the negative sign. So we have 0.5 centimeter all over as the absolute error. Then the relative error is 0.5 all over 50, which gives us 0.01. And the percentage error is 0.01 times 100, which is 1%. So it's a very small error. We have standard notation. That's like standard form. Scientific notation. A way to express a very large or very small number conveniently. So we have it to be n times 10 raised to power n, where the capital N is any number from 1 to 9. It must be less than, it must not be 0, and it must not be up to 10. And n is an integer. It can be negative 1, negative 2, can be 1, can be 2, 200 to 1 million. Like that. Examples: 300 million. To standard form E. So you move, just imagine that there is point at the end of this last 0. Then you move it back. The number of times you can go back till it reach the first number. So that is 1, 2, 3, 4, 5, 6, 7, 8. So we have 3.0 times 10 raised to power 8 meter per second. So when you are going back, it is raised to power positive. But now, when you are going to the front, for the 0.000056, you have 1, 2, 3, 4, 5. So we have 5.6 times 10 raised to the power minus 5. Benefit is that it makes calculation easier. It shows number of significant figures, and it is convenient for expressing very large or very small numbers. Yes, these are the prefix and the prefix that you need to know. You need to memorize them, right? You can ask question from any of it. Tera is 10 raised to the power 12. Giga is 10 raised to the power 9. Mega is 10 raised to the power 6. Kilo is 10 raised to the power 3. Deci is 10 raised to the power minus 1. Centi is 10 raised to the power minus 2. Milli is 10 raised to the power minus 3. Micro is 10 raised to the power minus 6. Nano is 10 raised to the power minus 9. And pico is 10 raised to the power minus 12. You can decide to write this out and memorize it. Try to come back and recite it again to be sure that you know it offhand. So, a quick tip: always check your dimensions. When verifying equations, pay attention to your significant figures in your final answers. Know how to calculate the least count for vernier caliper and micrometer screw gauge. Practice units conversions using prefixes. So memorize your prefixes very well. Don't spend much time on one question. If you don't know it, you can go back and come back later. Write it down on a paper and come back later. Double check calculations, especially for significant figures. Memorize dimensional formulas of common quantities like acceleration and force. Whichever you see in practice questions, memorize them. But whenever you are not sure, be fast in calculating them again. It's better to spend a bit more time calculating it than you're sure, and you end up getting it wrong. So you might just write it down and you are coming back later after you have finished the question. You can solve it to be sure. Practice past questions to familiarize yourself with the question patterns. Thank you so much. We wish you success and God bless you.